Hi, this is Dr. Kraus with an introduction to my random Bode problem generator. For my students, you can download this code off of Blackboard. If you're not enrolled in my class, you can, I'll put a link in the comments to a GitHub repository. So similar to my auto root locus one that I just posted a couple days ago, I've made some effort to try to come up with random but still what I would consider to be good Bode plot automatically generated stuff. And so exactly what I define is kind of my personal taste as to what defines a good problem. So you just kind of are executing through this, and then I think there's 4 different ways you could use this to study for a Bode related final exam. So one, you can get a random transfer function, and you could show yourself that transfer function, and then do one of 2 things. Try to find the Bode plot that goes along with that. So without plotting the Bode, you can look at the transfer function, find the poles and the zeros, and decide to do the Bode plot. And then after you've sketched it yourself, you would check it excuse me, by letting Python actually generate the Bode plot for you. And so here's the magnitude and phase of that random transfer function. The other thing you could do if you showed yourself the transfer function is you could then also say, okay, imagine that I had a fixed sign input to this transfer function. Once all the transient responses die out, what will be the sinusoidal, what I usually call Y steady state? It's really sort of steady state's kind of a misnomer in that it's sinusoidal, but it's going to have a magnitude and a phase that stabilize at some value. And so you could figure that out by evaluating the magnitude and the phase of the transfer function, multiplying by the magnitude of your input, knowing your input frequency, and you can get an expression for Y steady state. And if you did that and wanted to check it, for example, if I wanted to know what's the steady state output to a sinusoidal input at 1 hertz, I could do that. And if instead it was, say, 10 hertz, I could do that. And so that's finding the magnitude and the phase. It also is assuming an input amplitude of 1, but you could provide that optional input if you so desired. So that's how to use it. Excuse me, something's stuck in my throat. For the first 2 options of showing yourself the transfer function first. The other option would be to, what I just did, delete where it used to say G there, get a transfer function without looking at it, generate its Bode plot. Now, looking at that Bode plot, can you correctly infer the transfer function doing kind of a system identification type of problem? And additionally, if you picked a frequency, could you come up here and say, okay, at 10 hertz, for example, I can pick off a magnitude and I can pick off a phase, and it looks like at 10 hertz, I'm in the negative 60-ish, negative 70 dB, and so my magnitude, let me remind myself how I do that, whoops, and so 10 to the negative 70 divided by 20, I think I'm going to have a magnitude in the neighborhood of 0.0003, and my phase will be, well, it looks like negative 220 degrees, which I could remind myself how to convert to radians, although I forgot to put np.pi. And then I can say, okay, what is the steady state response? And for Bode plots, that's pretty reasonable to be off that far in the magnitude. And I said it should be negative 3.8 radians of trailing phase. Numerically, that's the same as this. So I think that's reasonable. So I can show myself the transfer function first and sketch the Bode plot, or I can look at the Bode plot and infer the transfer function. And I can also look at a Bode plot and pick different frequencies and try to find the steady state magnitude and phase. And then after I've done my system identification, I can say, okay, now I'm ready, show me the transfer function. And did I come up with that transfer function looking at that Bode plot? Thanks.